last session of the afternoon. I'm Mauro Werder. I'll be chairing here. And we'll start once we're ready. Okay, so this is Stefan Lenz doing the first talk on BoltzmannMachines.jl.
So hello, my name is Stefan Lenz and I want to present you the package Boltzmann machines. Boltzmann machines are a special kind of machine learning models, and we have several types of these models implemented in the package. The package is written entirely in Julia, but before I go to any code, I want at first give a short introduction to Boltzmann machines. Okay, it's not working.
Arrows.
So here it's changing, but on the screen it's not changing. Oh no, okay. So before I get to Boltzmann machines, let's take a look at neural networks in general at first. From a mathematical viewpoint, they are a special kind of weighted graphs, and they are inspired by the brain where the neurons are connected by axons. And some nodes are special nodes that receive the input, and they are called the visible units, which correspond to sensory receptors in the nervous system. The other nodes, which are called hidden units, correspond to the other brain cells, to the normal brain cells. The units are all connected by weights that are optimized with respect to a loss function, and usually this is done with a variant of gradient descent. This optimizing corresponds to learning neural connections in the brain. And the joint states of these nodes, so neuron may be on or off, activated, not activated, and this joint state of activation could be interpreted as ideas of the neural network. Boltzmann machines are now a special kind of neural networks. They also have visible and hidden units that are connected by weights. They're also inspired by the physics of ferromagnetism, because there are several parallels between the biological view and viewing grids of atoms with magnetic spin. So atoms have also positive or negative magnetic spin, like neurons have activation and no activation, and atoms are connected in the grid by a magnetic field, like the neurons are connected in the brain. And the spin of the atoms converges to a point of lowest energy, like the neurons converge to a learned state or to learned ideas during the learning process. The Boltzmann machines were invented in 1985, but as you can see on the graph, it took some time until they got popular. And the reason for this is because the formulation of the energy function and the probability distribution was rather simple, but it was hard to figure out how they could be practically trained. And I forgot to mention, so Boltzmann machines are especially for unsupervised learning, and they are not for classification tasks, and with this energy function, it is the goal to model the whole input of the whole distribution of the input. So, as I said, it was difficult to get to a good training algorithm for this model. So a first step was to consider restricted Boltzmann machines. These are Boltzmann machines that have no connections between the nodes of the same layer, And for those, there was a better learning algorithm invented that was feasible in practice, and it was called contrastive divergence. Then times later, the idea came up to stack the RBMs to form deeper neural networks, and that was the start of deep learning. Each of these layers in the deeper network can then capture higher level ideas. For example, in facial recognition, there is the first layer usually captures edges in images, then upper layers can recognize more complex structures like face parts, nose or mouth, and then until this goes up until an individual face can be recognized. These stacks are trained that the first RBM gets the actual input, and then the next RBM is trained with the hidden activation of the first RBM, and so on. These stacks of RBMs can now be interpreted as Boltzmann machines, and then they are called deep Boltzmann machines. It was discovered that this RBM stack is a good starting point for starting a joint training of the whole stack as a Boltzmann machine with an approximation of the training algorithm for Boltzmann machines. It is done after the stack has been trained. This Boltzmann machine training algorithm is done with a mean field approximation algorithm. Otherwise, this general Boltzmann machine training algorithm did not work so well. This was described in 2009 by Solakudinov and Hinton. And when you took a look at the graph, you probably wondered, so why has the trend stopped? And why did it even go down in 2017? So this is because other algorithms gained popularity, in particular for image classification, which is the main task for machine learning, and we also have heard many talks about this in the JuliaCon. So for this task, convolutional neural networks are now the state of the art, and you wouldn't use Boltzmann machines as a precursor for an image classification net, which has been done before when there was not so much data available, not so many labeled images on the internet that you could, with pure mass of data, train the convolutional neural nets. So sadly, because we want to image classification, I can't show any more cat pictures. But you might ask, why should we then even bother with Boltzmann machines if we can't do image classification? So there are several strengths that Boltzmann machines have, and they can, at one point, they can model different input data type. A standard input data type is a binary, but you could also model categorical variables, and there are subtypes for continuously valued variables. You can do unsupervised learning, which means you don't have to have labels to learn useful things from data. You can just put the data in by itself. And the Boltzmann machine model is a generative model, which means you can generate artificial data when you have a trained model. They are also able to deal with smaller sample sizes, as I said earlier, and these properties make it especially useful for medical data sets, where you have, for example, medication, diagnosis, and laboratory results, questionnaires, and genetic data, and want to analyze those, which are not that which you don't have that big sample size than you have, for example, images from the internet. But here I want to go to a more relatable example in this talk and see whether we can train the Boltzmann machines on cooking recipes and see whether it can see which ingredients go well together. So I have as a prerequisite, I have here a compiled matrix and some collection of recipes. In each row there is one recipe. In the column there are the ingredients, and there is a one there when the ingredient is mentioned in the recipe. So now we have this data, and we can have our first code slide and train the Boltzmann machine with this data. So we have the matrix, the data matrix, call the package and call the function fitDBM and get a trained network. So what can we do now with this the Boltzmann machine? A first use case is dimensionality reduction. So when we have a Boltzmann machine with only 2 nodes in the top layer, as you see here, then we can present each sample, so each recipe here, to the network, induce activation in the network, and then we take a look only at the top 2 nodes and take the linearized activation that is induced there, and we get a point in 2D from our long vector. Then we can plot this, and on the x-axis of this plot you see the activation of the first node, in the y-axis the activation of the second node, and each recipe is 1 dot. And the dots are colored whether they contain the ingredient that is in the title or not. When we take a look at this, we can see some patterns. In the first row, the pepper probably indicates the more savory recipes, and sugar is more contained in the sweets, but it is also contained in many savory recipes. So you could say, when you take a look at these plots, that the network somehow got the idea of savory versus sweet recipes, because they are contained in separate clusters. In the second row, you see more structure in the data has been discovered by the network, and one might wonder what this could be. But how does one get to those plots? So when I showed this simple training call, it was a little bit too simple and I cheated a little bit. So when you take a look at the documentation of the fitDBM function, you see that there are many more arguments to it. And I also had to use some of those arguments to do the call that resulted in the DBM that was used for the plots. So here you can see now there are arguments, especially learning rate, which is a parameter for the gradient descent. And it says how far you go into the direction of the steepest, in this case, ascent in one training step. And you see the number of epochs. That is the number of times that each data sample is presented to the network. Then you have the number of layers, and so how deep is the network, and for each layer, which number of nodes is in the layer. The epochs and learning rate can be specified for the pre-training and for the joint training separately. But this looks kind of arbitrary, and so why exactly these parameters, and what are good parameters for the learning? So in supervised learning, it's easy to say when a model is good, because you just take the percentage, for example, of correctly classified images, and you have a clear number that states, oh, my model is that good. But here, it's a little bit more difficult in unsupervised learning, and with Boltzmann machines, we have as a main evaluation criterion the likelihood. So that says how well the network captured the distribution of the input data. The problem with this criterion is that it is computable only for very small models, because the computation time grows exponentially with the number of nodes. There is a stochastic algorithm available for the likelihood estimation, and it is implemented in the package. It's called annealed importance sampling. The problem with this is that it is also only an estimation, so it's not it does not give the exact value. There's always some uncertainty, and it's also quite time consuming. So more commonly used in restricted Boltzmann machine, because it is fast and behaves probably similar to the likelihood in restricted Boltzmann machine, is the reconstruction error. You calculate it like this, that you have the input, then you go up one to the hidden units, induce activation, and then you get again the activation of the visible units, and take the difference, the absolute difference between the activation in the beginning of the input and the induced activation. So now we can use this evaluation in the training process and see how well the training process works. So in the beginning, we split our data set in a training data set and a test data set. And then we initialize some monitor objects that then will be used to gather all the monitoring information that is collected during the training. We can use these monitor objects by in form of a closure. We just have this anonymous function in the monitoring argument, and we give the anonymous function there, and we collect all the reconstruction errors of the different layers during training. And for the joint training below, we have a function that executes the annealed importance sampling and estimates a lower bound of the log likelihood during the joint training. Then we can plot this function with the accompanying plots package, which is based on Gadfly, and we get these plots. So here you can see there are 3 plots for the 3 RBM layers, and you can see the reconstruction error, and it should go down. And there is 1 plot for the joint training. It measures the lower bound of the log likelihood, and this should go up. And because it is estimated with a stochastic algorithm, you can see there is some uncertainty in the estimation that is indicated by the ribbon around the graph. Because of the design that you can input here any function into, you can inject any function into the training process. You can also use this, for example, to create a progress report, and here put out the progress indication when the first layer has been finished, or you can also do progress report for each epoch if the model is really has to deal with much data. Now let's see whether we can answer the question what goes well with eggplant with our model. And for this, I want to use conditional sampling. The sampling, the data generation in a Boltzmann machine is based on Gibbs sampling, which is a Markov chain Monte Carlo method. And it requires some steps to be run, and you can specify how many samples you want to get. Then you have to find which variable stands for eggplant, and initialize some activation. Here you can see the variable particles, which is also because of the inspiration by physics named like that. And this has the activation of all the neurons in it. And then we do all the sampling steps, and we keep the variable eggplant fixed at activated state. And after that, we get a number of recipes that we generated by that procedure. And this is now a word cloud of what the DBM chef suggested here. It looks delicious, I would say. So this recipe example only needed a very simple architecture, but with our package, it's also possible to have more complex architectures. And we only had binary variables, but we can also have different input data types and combine them together. That's the multimodal architecture then, which is also possible. You can have, for example, binary data type, which is here indicated in blue, and for example, yellow as Gaussian input, so as continuously valued input. So this is useful, for example, in the medical setting, where when you want to combine diagnosis and lab results. Diagnosis you would usually encode in binary format, and then the lab results will always usually be continuously valued variables. Or to stay in the recipe setting, if we want to add, for example, cooking and preparation time, rating of the users, calories and cost, variables like that to the model, then we would also be good with a multimodal architecture. And also it has the advantage that when you partition layers, you have to estimate fewer parameters, which makes it more useful for if you have even smaller sample sizes. So it is also useful when you have only one data type but small sample size. How can you define now these architectures? So for a simple, as a basic DBM, you can specify the number of hidden units as an array, or you can specify, as we have seen before, all the parameters for each layer individually. Then, if we have partitioning, then we also have the same philosophy, that we have the RBMs as basic building blocks that are organized in an array, and the first element of the array here would be then a partitioned RBM, which correspond to a train partitioned layer argument. And here we can see that we have to also specify the visible nodes for the partitioning of the input, and here we can specify another type for modeling continuously valued variables. It is to say that the modeling of continuously valued variables is still a research question, and is still subject to research, how you can really train them well. And we also want to contribute to the research in this field by making it easy to train these types of Boltzmann machines, so that you can play around with this, and you have the monitoring, for example, that makes it easy to hook into the learning process and see what's happening and how the learning is going on. Then we have another example of how you can hook into the whole process of optimizing. here is an example of regularization. That is not really useful probably for Boltzmann machines, but it's a general technique, and it's only here for demonstration, so how you can write your own optimizers. So here we want to write a new optimizer, and we take the standard optimizer that optimizes the likelihood, and we wrap it up into our regularized optimizer and delegate most of the functionality to the default optimizer, but in the gradient computation we now compute a different gradient, and we account for the size of the weights there. So, and this new regularization can be used for RBMs, and at the same time, the same thing can also be used for DBMs, because because of the stacked structure, you can apply it layer-wise. So why did we use Julia for all this? Because it provided out-of-the-box performance without extra framework, so we didn't have to leave the box for this. And Julia provides good scripting language features, which made it very easy to hook into the process, for example, for the monitoring, to just give a monitoring function and execute it after each epoch. And also it has good capabilities for parallelization on compute clusters by using PMAP. So with this you can evaluate many models in parallel. And this is very useful because it is I didn't go into the details of the training algorithm, but it is a stochastic algorithm, so every time you run it, you will become a slightly different result. So to get consistent results, it's necessary to run usually many models in parallel. And then it is possible to reuse memory, which in this case, because all the weights operations are matrix operations, is very important to reuse the space, because otherwise it will get very slow. And with the function mul, or formerly a mul b, it was possible to have control over the memory allocation, and thereby we were able to incrementally optimize our algorithm. At first we could simply write it like it was in the papers, but then slowly reuse memory, and this really increased the speed greatly. What we would hope for, and in the future, would be more explicit multi-threading. So for example, the optimization of the different layers could in some for the joint training could be done in parallel. So here it would be very useful to have threads operating in parallel. Also very useful would be or a user-friendly compilation, so that you can have the trained models and put it easily into apps and deploy it somewhere. And with that, I would like to conclude and thank you for the attention, and I hope there are some questions.
Yes, are there questions? Yeah.
So is the training algorithm you do a layer by layer contrastive divergence?
That's the first step, and then there's a more complicated Boltzmann machine optimization, which I didn't go here into detail because it's a little bit mathematical with the mean field approximation, which is another algorithm. So basically it's like that. The problem is that all nodes are connected by other nodes with each other in the layers, and it is a very hard problem to calculate the actual activation that is induced by a visible, by the activation of the visible units, for example. So this is very hard, and in physics there was also this mean field comes also from physics, where you have all the atoms or all the bodies that are influencing each other, but you take only into account the next ones. So you make only an approximation of the complex interplay of all the neurons together. And this approximation is then done during the joint training and the Gibbs sampling, and these two are then, they're the two elements that have to go together. So it's, yeah. Okay. Probably, so I left it a little.
Initialize it, contrastive divergence, and then you minimize like something like the negative elbow?
Yes, that's correct. Yeah. Okay. But that is exactly, that is done with the mean field approximation and the Gibbs sampling step. So there, yeah. But I couldn't go into detail because, yeah. So okay. that.
Is there a way to figure out how much each of the original inputs contributes to the final results, namely the 2 or 3 or however many you have in the last layer?
I'm not sure if I understand it correctly. You mean, so which sample contribute most to learning? Or
not which samples, but which features? Which of the original features fed into the deep belief network or DBM?
The features are more or less, yeah, they are learned in an unsupervised manner. So it is possible that the DBM picks up some. It also very depends on the architecture. So, for example, you have to also play around with the number of nodes. And these are also very important in how intelligent the net is, or for example, or it has to also depend on the data. So how much structure is in the data, and how deep do I have to make my network to capture that structure? And it's also not something that can be answered in a universal way. So it has to be tuned. It has to be seen whether the network is complex enough to capture the structure that is in there.
Okay, I got one question. So could this be used as a backend to other kind of machine learning frameworks, or not so much?
So I mean, it has a DBM. It has the fitting function. So you can use this model, for example, and generate data and use it otherwise, and for example, to generate new data or something. But yeah, the possibilities are unbounded. Okay.
Cool. Well, thanks, Stefan, again.